Hey everybody, it's Ripley back again. We're going to talk about double integrals over general regions. So now that we know how to take double integrals, and they're pretty easy to work with, right? They're kind of cool. We're going to have a little bit of fun. So let me just give you an example of what I'm talking about here, because if you recall from before, what we were doing is just taking the regions. So here's my x. Hold on, let me get squared away here. Here's my y and here's my z. My regions were bounded by rectangular regions down here in the domain on x, y, right? So z equals f of, I like to beat this into you guys, so bear with. All right, so let me show you what I'm talking about. This is actually kind of cool, and to generalize it is actually quite simple. So let's say that I have a function that lives up here. This is going to be my surface, all right? I'm trying to get better at these. You guys are going to laugh. All right, so this guy is living, we'll dot this out a little bit so we can't really see. It's kind of living, all right, yeah, that's pretty good. All right, it's kind of living here in the first quadrant. I don't know what its name is. It's just going to be f of x, y, all right? Now, when I'm taking a double integral over a general region as opposed to a rectangular region, what I mean by that is, remember our good friends, let's say f of, let's keep it super simple. This is y equals x squared. And let's go, what did we do before? Let's just go y equals x. So this is going to be y equals x. So in the xy plane, if you recall this, we used this thing a ton of times in Calc 1, it looks something like this. So this was y equals x squared, and this was y equals x. And then what we're doing, I need that to be bigger, don't I? I'm going to exaggerate it a little bit. Sorry, you guys, just give me a sec. I won't rewrite the functions, I promise. I'm going to waste your time. I'm going to exaggerate it a bit more. So I'm going to have this guy go like that, and I'm going to have this guy go like that. Okay, perfect. So now what we're doing is, when we take this double integral over this general region, I mean, if you think about it, if I bring this up here, and I think of sort of, it's not a level curve, but what's happening is there are points all along this region and in this region that map directly up to f of x, y, right? So what I'm looking for is, if I drop these, I'm just sort of arbitrarily choosing where this is going to go. I'm dropping sort of this curtain. Let's think of it as like a curtain down here, right? And then we're finding the volume of this guy right here. So how would we do that? Well, let's write it up. Let's write it up fancy. All right, first and foremost, I know that the volume is going to be the double integral over d. Remember, d lives down here. There's lots of things to remember, and this is going to change on us a little bit down the road. But just be patient with me, all right? So this would be, f of xy dA, right? And remember, this turns into the double integral over d of f of xy d. Now, we've got to be careful here. Remember, I can write this as dy over dx. I can go either way with it. But I'm going to write it as, first thing I'm going to do is I'm going to write it as dx dy. Or maybe dy over dx. It doesn't really matter. But we are going to have to think about how we did it in the past. What are the bounds? What am I bounding this region by? Because this is clearly a closed, bounded, closed meaning I don't have any holes, I don't have any discontinuities, and bounded means I can just draw a line around it, right? So how would we do this? Well, let's think. I know that this runs, if I want to figure out where these points of intersection are, I know that that's going to happen at 0, 0, excuse me, and I know that this is going to happen where? At 1, 1. True? You agree with that? So x is going from 0 to 1. But I've got these functions of x. So what should I do? Like, how should I deal with that? Well, it's actually pretty easy. Let's actually, I'm going to have, let's see, what do I want to do here? I want this thing to be interesting. I'm going to let f of xy equal xy plus 1, okay? So when we're in the first quadrant, when we're living in the first quadrant of the xy plane, it should be relatively obvious that z is going to be positive. And the way in which this is written, because that can be a little bit strange, what we're going to do is we are going to find, we want the volume of solid, because the way it's written can be a little bit tricky. That lies under f of xy, okay, and above above region D, defined by, I'm going to get fancy, this is going to be the set of xy such that xy, let's see, how do I want to write this? Set of xy such that xy lives between, well, it's going to be bigger than x, right? And less than or equal to, it's going to be greater than or equal to x and less than or equal to x squared. You know what? I'm going to write this a little bit differently. I'm going to write f of x is between these two guys, right? And then x is going to be between 0 and 1. Now that's a little bit cumbersome. Sometimes you would just say it's bounded by. So there's a better way to write this, and that's why we say bounded by, because I can incorporate all of this into one word. So let's just take an arrow down here and say bounded by f of x equals x, and f of x equals x squared. All right? All right, so watch how easy this is. This is kind of fun. Except writing this thing up can be a little bit tricky. So volume is going to equal, I'm going to have a double integral. Now, what are the limits of my double integral going to be? And I got to be a little bit careful with that. One thing that I know, let's just do this for free. I'm going to write my integrand in here because that's my f of xy. Okay? Now, you kind of have to keep an eye on the prize, but you only have to make this mistake a couple of times before you start flipping these guys around to get it just right. I like to deal with the y first. So I'm actually going to do a dy and a dx. Now, think about this. If I'm going to do a dy first, if I'm going to deal with this as though it's just a y, excuse me, then when I'm done with this little portion of my integral, I need everything to be in terms of x's. If I'm going to find a volume, right? I can't have y's hanging off the back. Whoa, dropped my stylus. Sorry, guys. So I got to think about that. What am I going to do? Well, I want y's to disappear and become x's. So I'm actually going to go from x to x. Whoops, did I do x squared? I'm an idiot. That's the square root of x. Oh my God. Sorry, guys. Moron. Don't mind the weirdo. Sorry, guys. This is going to be square root of x. That's one that you get to catch earlier. Square root of x. I don't know why I'm doing it up here, because this is a heck of a lot easier just to describe it this way. Jeez Louise. I'm sorry, guys. My first video of the day, I'm a little punchy. Okay, so we got it. So I'm going from x to root x. All right. Now, these outside limits are on x. Well, that's cool. We know that we're doing this between 0 and 1. Okay. Now, in the book, what it would say is, let your volume equal the integral from a to b of the integral from f of x to g of x of f of x y dA. That's what it's going to say. But, I mean, we've worked with these types of curves intuitively before, and I promise you that any curves that are going to be given to you in this section are going to be relatively easy to work with. Okay. So let's actually go through this thing and find the volume. So I'm going to deal with the inside integral first. So I'm going to write integral from 0 to 1. And then I'm going to go, I'm going to use big fat parentheses throughout so I don't make any errors. All right. Remember, that's a y. Anything that's not a y, I treat as a constant. So this is going to be x, y squared halves plus y from x to root x dx. Now, right now you should be going, oh, I see why I got you, Ripley, you crafty devil. Well, if you look close, can you see why I did it? Now, everywhere there's a Y, I'm going to stick in, I'm going to change colors, I'm going to stick these guys in. So after this first step, all my Y's are going to disappear, and then all I'm going to have are X's, which I can then take the antiderivative of relatively simply. So let's do that. It's going to be integral from 0 to 1. Now this is, I said before, I'll say it again. This is where it gets a little bit tricky because I just have to be careful what I'm doing, okay? I just got to take my steps super slow. So square root of x squared is x. So that appears to be x squared halves plus root x minus quantity x cubed halves plus x, right? Does that look right to you guys? Heck, I'm just going to be lazy at this point, right? Because I don't have anything that I can really combine. So notice all the y's are gone. I'm right where I need to be. This is going to be x cubed 6 plus 2/3 x to the 3 halves minus x to the 4th eighths minus x squared halves. Everybody agrees? We're looking pretty good? I go from 0 to 1. I don't have to worry about 0 because everything drops out. And I get 1/6 plus 2/3 minus 1/8 minus 1/2. It looks like 24 is going to be my common denominator. Does that smell right to you guys? So what's that? 4 plus 16 minus 3 minus 12 minus 15. What is that? This is all over 24. Sorry, guys, I just don't want to change pages right here in the middle. 20 minus 15 is 5 24ths. And this would be cubic units, right? Does that make sense? That's pretty easy, right? Okay, now, we do have this problem. So I'm going to draw the same. Hopefully that was easy enough. What happens here? Okay, what if I do, let's go, I gotta think this through. I don't want to get you guys all kinds of screwed up. I'm actually gonna extend this guy, these guys here for a sec, because it'll be easier. So this is z equals f of xy. I guess I shouldn't have used f back there. Call me a bad man, I reckon. And this is gonna be y, okay? What happens if I have that same, yeah, you guys understand what I'm sort of yelling at myself for. This shouldn't be f of x, nor should this. This should be, I'm going to change those right now just so you guys don't yell at me. Let's go, I'm going to say g of x here, and then I'll change these. See, I have to call myself out with when I make errors. There's a lot to keep track of, man. I make mistakes all the time from g of x to h of x. Okay. All right. Okay, now I'm going to draw the exact same curve as I did before. I'm going to see if I can get good at these. Wow. Or maybe not the exact same curve. And then, right? And this is just a piece of this. All right. Let me dot that out. Make it look pretty. Okay, now check this out. What happens now? Come on, give me some color. If I have this curve, and then I have this guy going straight across. So let's say that this is x equals y squared. Excuse me, goodness. And this is x equals 2. Now, let's try and figure out what exactly we're looking at. Well, they're gonna, if I bring these up, think of this as like a curtain that's going up into our region, into our curved region, and then I've got, I'm gonna have sort of this, this badly drawn thing up here, and oh, that's awful, I'm sorry, because I don't really know how this thing is being warped, but what we're looking for is the volume, as if this thing were casting a shadow down onto the xy plane, and then we took the volume of all the space between the surface and the region. But hopefully your spidey sense is tingling here just a little bit, right? Well, if I put this, if I put this on just the Cartesian plane, what am I instantly in trouble with? Well, this is not a function of x. It is, however, a function of y. This is not a function of x. It is, however, a function of y, right? Remember, this is x equals 2. This is x equals y squared, right? And then let's see, where do these guys meet? This is at what? This is 2 comma root 2. 2 comma root 2 and 2 comma negative root 2. Now this for me is where I really have to slow down, because now I'm no longer talking about functions of x, I'm talking about functions of y. So how do you think that's going to play out when we start looking for functions, or excuse me, for volume? Well, let me draw it up fancy. So the volume is going to be the double integral over d. Remember, d is this region in here. We'll call that d, right? And then I'm going to have, just like before, f of x, y, dA. But remember back here, what I had was a dy on the inside because these guys were functions of x. And I needed my y's to go away so my dx could work on them. Well, now I've got functions of y. You may say, well, Ripley, why don't we just solve for y over here? Well, we've learned that's not a great idea, is it? Because then I double the amount of work that I have to do. I can kill a bunch of birds with one stone here. So what I'm going to do is I'm going to do the integral. This time, well, let's just go, I know that I'm going from, what are my values of y? Well, I'm going from negative root 2 to root 2, right? And then I can, as I did before, well, sort of, I can go g of y to h of y, right? Then my f of x, y. Now I got to think here, what goes where? I want to put a dx here because I want my dx to turn into y's. And then once everything is in terms of y's, then I can let the dy go to work on it. So I'm going from the lower to the upper. So this is easily writable as the integral from negative root 2 to root 2 of the integral of what? Well, clearly, if I've got f of y's, then the bigger functions are going to be farther to the right than the little ones. So the small one would be y squared. The upper one would be 2. And then I'm going to put in, let's use the same one as before, if you guys don't mind. I'm going to go x, y. I think it was x, y plus 1, wasn't it? Only now I'm going to go dx, dy. Now let's see what happens. So again, change colors here so I can play. I'm going to deal with this first. By the time I'm done with this step, I want everything to be in terms of y's or constants. No x's allowed. What is that? That's negative. Okay, root 2. We're good. So the integral from negative root 2, can't read my own darn writing, all right, to root 2, excuse me, of, all right, dx's. So whatever, this y is going to be a constant, so I end up with x squared halves y plus x, big parentheses, from y squared to 2, dy. What's that equal? Integral from negative root 2 to root 2 of, now be careful here, right? What am I putting this into? I'm putting it into the x's. So I'm going to end up with 2y plus 2 minus, and then what do I get? Okay, I'm sticking this in for the x, so I'm going to get y to the 5th halves, right? Plus y squared. You see it? Now, I always have to double check myself. I'm like, wait, did I put those in right? Right? X gets a y squared, I got the y squared. X gets a y squared, I get y to the 4th times y. Okay, whew, I'm good. All right, what do we got here? We got a constant, we got y squared. Oh, cool. So now I'm going to respect the heck out of that negative, as always, and I'm going to take me an antiderivative. I'm even going to change pen color. Ooh, I haven't used the lavender. Let's use the lavender. All right, so what's this thing turn into? Y squared plus, oops, what are you doing, Ripley? We're doing with the x's now. That's, whoops. We're not doing with the, I was right the first time. See? Slow down. I got to slow down as well. A little too much caffeine. That should be a dy, right? All right, so y squared plus 2y minus y to the 6th 12ths minus y cubed thirds. I just distributed the negative through. From negative root 2 to root 2. All right, this is going to be a little bit uglier than the last one, but let's check. This is going to give me 2 plus 2 root 2 minus, what is that, 8 twelfths, right? Square, yeah, 8 twelfths or 2/3 minus 2 root 2 thirds, right? And then minus paren 2, that's cool, minus 2 root 2, minus, what is that? 2/3 again, right? 2/3 again. You guys are, of course, going to yell at me, hopefully. And then this is going to be plus 2 root 2/3. 2 root 2/3. All right, let's see what goes on. This I'm going to turn into a plus, a minus, a plus, and a minus. These guys cancel. These guys cancel. And I end up with 2 root 2 plus 2 root 2 is 4 root 2. I get minus, what is that, 4 root 2/3, which is 12 root 2/3 minus 4. That's 8 root 2/3. And that's how she works, which is pretty cool. Now, I'm not going to go through an actual integral with this last little piece, but I do want to address this issue. Like, what happens? Let's say that your region in the xy. Now, I'm not going to do the z-plane. Let's just go x and y. Okay, and let's say that it's something crazy. Let's say that it does something like this, and then, I don't know, something like this, and then it drops down like this, and it goes whoop, like that. Okay, let's say that's a vertical line, by the way. I'm calling that vertical. Now, I'm going to call this vertical at x, at x equals a. This is going to be at x equals a. And then I'm going to call this the all hell breaks loose part at x equals b, right? Now, why do I say that all hell breaks loose? Well, we lose our function, right? This thing, I was fine here when I could subtract if this is g of x and this is h of x. From a to b, I'm golden. I can subtract g of x from h of x. You remember this when we were doing that, when we were dealing with functions before. Now, all of a sudden, this thing gets really ugly. Well, but that's not really a problem, because let's call this region 1. Actually, let's not even call it region 1. Let's call it D1. Let's call it D1. D1. And let's call this D2. Now, we're allowed to do that, right? I mean, we can always bust areas up. Now, floating at you somewhere out above this plane is our z equals f of xy, right? So what we got to think about, if we're looking for the volume that's created for this ethereal, I don't know, let's do it dotted. I like the lavender. You know, it's floating up above somewhere, right? It's doing something crazy. Who knows? And what we're doing is we're looking for the volume that sort of, again, think of it as like a shadow that's cast down onto this region, and then we're taking the volume of that space, as it were. Well, what we do is, probably predictably, hopefully, is we take the first part just like we would in the prior examples. I would let the volume equal the integral over, now this is going to be d1 of f of x, y, and then remember, if I've got h of x's and g of x's, then those guys are going to go here, and this would be dy dx. So I'll do it in the next one. Then what would I do? Well, I now have to take the other integral over d2, but now I don't have functions of x that define d2. I have functions of y that define d2. So now I would still go f of x, y. This thing never changes, but now I'm going to go dx, dy, if that makes sense. Hopefully it does. I mean, what it takes is a head shift right in the middle of the problem. And we'll get to play with these. These are actually quite fun. I really enjoy this section. It's a blast. Okay, hopefully this was helpful. Sorry about the mistakes earlier in the presentation, but hopefully I fixed those. So I will see you in class tomorrow, and we'll start having some fun with double integrals over general regions. Have a great day.